We're going to look at improper integrals today. An improper integral is an integral that involves infinity or an infinite discontinuity. Example here, consider if we have this graph of 1 over x squared. That graph is located down here. You can see what it looks like. It's above the x-axis, and they want us to find a integral where it starts at 1, so you can see 1 down here, and goes to some other value t where t would be greater than 1. So you can see from the graph down here that no matter where that t is, we should be able to find that area in there. So how you would do it, just like we normally do integrals, find the antiderivative of this. Be easier to think of this to find antiderivative as x to the negative 2. So if we add 1 to that, that'd be x to the negative 1, but we got to put reciprocal out front. So that's what we got here, just written with positive exponents. And then we want to evaluate that from 1 to t here. So you can see 1 to t located there. Now if we plug that in, with the upper limit minus the lower limit, you would get, or what we'd end up getting here is negative 1 over t minus the result of when we plug 1 in, which would be 1 over 1. If we double slash that, that ends up being plus. 1 over 1 is just 1, and if you switch them around, you get this result. So the area under this curve is always going to be 1 minus whatever this t value would be, and that would be the area. So for example, if t ended up being 2, then the area would be 1 minus a half, or a half would be the area right here. If t was let's say 6, okay, then the area would be 5, 6 if this was from 1 to 6 here. So no matter what it is, we could figure out the area doing it that way. Well, what we're going to look at next is what would the area be if we made this infinity? What's the area from 1 to infinity? So what we're going to do in situations where you get one of these improper integrals with infinity is we are going to replace the infinity with a t, and then figure out what's the limit of this integral as t goes to infinity. So if you do the same thing we just did, we know this came out to be 1 minus 1 over t. So now we're looking, well, what do we get here as t goes to infinity? Well, if you put infinity over in there, remember 1 over a very large number, that's going to approach 0. Just like if you have 1 as we approach 1 over something as it approaches 0, that would be infinity, because 1 divided by a very small number would equal infinity. So basically up there we get 1 minus 0, which would be 1. So the exact area under that curve from 1 all the way out here to infinity, even though that graph never touches the x-axis, the area is exactly 1 if you do that. And you can see those numbers do get closer here. If the limit's 2, you get 1/2. If you go out to 3, the area becomes 2/3. If you go out to 5, 4/5. We saw what you get when you put 6 in there. We got 5, 6. You can see all these areas are getting closer and closer to 1. So sometimes you can integrate and find the area, the exact area, even if you go out to an infinite value, and that's improper integrals, what we're going to be looking at. So definition here, anytime you are approaching infinity, we want to come up with some other variable as t approaches that and replace the infinity with that. Solve the problem and then take the limit and see what you get, provided that that limit exists as a finite number. You can do it with negative infinity too. If it's negative infinity, then we're replacing that again with a variable and doing the limit as you approach negative infinity. On ones that you have infinity on both, so you got negative infinity and positive infinity, then we have to split that up. So we're going to take a number in between and have this go from negative infinity to that number, and then add it to another one where it's that same number to infinity. So we'll split it up as 2 and then do the limit of both like we did up top here, and see if that, again, it comes out to be a finite number. If it does come out to be a finite number, that is called a limit or an improper integral, then that is convergent. If the limit doesn't go to a finite number, then we say this is divergent. It's a divergent one. So those terms, convergent, divergent, you will hear those throughout the year. Let's try one out. So determine whether this integral from 1 to infinity of 1 over x dx is convergent or divergent. So first thing we're going to do, we're going to write this as the limit, and we'll use t here because that's what the notes had been using, but you could use anything. And we're replacing that infinity with a t here of 1 over x dx. All right, so next we're going to find the antiderivative here, and we know antiderivative of 1 over x is natural log. So this is going to be the natural log of the absolute value of x evaluated at both t and 1. So now let's plug in there. So now we got limit as t approaches infinity. This would be natural log of t here minus natural log of 1. Natural log of 1 is 0. And the other one here, as t goes to infinity, if we put infinity in here, what's the natural log graph going to do? Well, we've seen that natural log graph before. Graph of natural log looks like this. So what is that approaching as we go, as this graph goes out to infinity? What's this approaching? Well, it's going to keep getting bigger and bigger and bigger. So that's infinity. So here we got infinity minus 0, which would be infinity. So on this one, we would say this is divergent. It's not approaching a finite number here. There's an infinite, on this graph here, there's an infinite amount of area under that curve. It does not approach a finite number. So what we've seen now is that in the graph of 1 over x squared, when we did that graph a little bit ago, we saw that that was converging to a number. That exact area we found there from 1 to infinity ended up being 1. If we do the same thing with the graph of 1 over x, this had an infinite amount of area. It was not finite. This one diverges, whereas this area was exactly 1. So what we can conclude or figure out here is anytime you are doing one of these where it's like 1 over x to some power, if the power is greater than 1, you get a convergent one. So if this were the graph of 1 over x cubed, or 1 over x to the 4th power, or 1 over x to the 5.5 power, anything bigger than 1, you're going to get one that converges. If this is exponent of 1 or anything else, it's going to be divergent. So 1 over x is divergent. If you have 1 over x to the half power, that would be divergent. Remember, that would also be the same as 1 over square root of x. That would not converge. 1 over x to the 1/3 power would also not converge. It'd be divergent. That would be the same as cubed root of x. So any of these ones are not going to have a finite amount of area. It'd have infinite area underneath.